What chapter are we on?
Okay, so chapter 10,
479.
we're going to have an AC motor working, and now we're going to have a stator, which is going to be a stationary portion of the motor. We're going to wind some windings around it, and then we're going to have a rotating portion. We're going to have a rotor. That's going to be a rotor rotating around some shaft. The shaft is going to be the thing that go roundy roundy and make the fan go or whatever. Now, if you think about the nature of three-phase power, you have one phase that's doing something like that, and then you have another phase that's 120 degrees out doing something like that, and then you have another one that's another 120 degrees out doing something that looks like this, and now you have those phases going right after the other. Our motor that we're looking at here is only using one of those phases, but the magnetic field that's sitting on the stator is going to be north over here, south over there, south over here, north over. It's going to change 60 times a second. So I've got a magnetic field that's building up and then going down and then going the other way and then building up, going down, going the other way 60 times a second. That changing magnetic field is going to cause currents to flow on the rotor. So the induced magnetic field, the magnetic field from the stator, is going to induce currents to flow on the rotor. Those currents that flow on the rotor in turn are going to create a magnetic field on the rotor. That magnetic field is now going to follow the magnetic field of the stator. Now on a synchronous motor, that following would be exact. So I would be, if this is south, then that would be north. And if this is north, that would be south. And as I changed directions, I'd follow it exactly that way. On a squirrel cage motor, which is the type of motor we use in our lab, what happens is I have slip on the motor. It's not going at the same speed as the rotating magnetic field. That difference is what's causing my torque, causing more current to come, causing power to be generated by the motor. Now, I can generate electricity in the same manner as I use it. So on your car, you have an alternator. The alternator can either be a generator or it can turn the crankshaft. It can be a motor. It can go both ways. That's what's called an alternator. It alternates between those two functions. Anyway, so what's happening here is a very complicated thing, but we'll try to keep it as simple as possible. So now I look at it, and I have north-south, and I'm going to rotate my north part of the winding to wherever south is. When I go and I change the north-south, because as I change my voltage, I go from a positive voltage to a negative voltage. I change where my north is. As I pass through zero, I don't have any magnetic field at all. So this thing is going to be free floating out there. I started moving. An object in motion tends to stay in motion, right? So it stays in motion, rotates through a little bit. Now I start building up the north and the south the other way. I have maximum north, maximum south at my peaks. I don't have as much when I get towards zero. So that's what I'm doing. I'm alternating the magnetic field, making the rotor rotate in the middle. Now, I can do it with two phases. So now I have a two-phase motor, and I have the A phase and the B phase. So if I go back and look at this guy here, and I say, well, here's my A phase, there's my B phase. A is going to be north, and then B is going to be north. And then A is going to be north, and then B is going to be north. A, where's A? B, A. So my maximum north, I'm going to build up, this guy's going to be maximum north one way, and then this guy's going to be maximum north the other way, and then he's going to be maximum north on the negative side, and then he's going to be maximum north on the negative side of the B guy, and my north is following around in a clockwise motion, and that's why you hook your motor up A, B, C to T1, T2, T3 so that it rotates the right way in a three-phase world, and I'm sure we'll see a three-phase world pretty soon. Two-phase motors you can buy them, but they're not all that common. Let's see, what do we want to do? I want to go to there. So now we're seeing my phases are changing and my rotational position as I rotate around through the phases as they change. And again, if I'm a synchronous motor, I'm following that magnetic field exactly. It's going to rotate 60 times a second. I'm going to rotate my shaft 60 times a second. But on a squirrel cage motor, I'm going to slow down, have some slip, be rotating at a different speed. All right, well, you've had to deal with the connection powers coming out of these things. You haven't had to deal with the housing much, except to get keep your pieces of copper out of it, right? We've only burned up, in 10 years, we've only burned up one motor because we've allowed our stripping of our copper wire to go into the motor and short it out. So that's pretty exciting. The motors we use are only $250 a piece. It's not like they're very expensive. When you get to bigger motors, then that could be an issue. You have an end plate. The end plate has a fan associated with it. You've probably seen that. You have a bearing on the housing. You have a stator. You've seen the stator windings if you've looked. And then you have a rotor rotating in the middle. You have some way to connect it. You have a key on your shaft, so you can and a key way to make sure that whatever you have it hooked up to stays in position. You know? And a lift ring, because the ones we have, we don't need a lift ring on. But the smallest motor on a submarine is 10 horsepower. The biggest one is 200 horsepower. Well, you're going to need a lift ring. You're going to have some way to ring it in and out. In your usage, the stator windings and the windings of the rotor are things that you wouldn't deal with much. In a submarine usage, in a Navy usage, those things get replaced every 5 years. So every 5 years, all the motors get ripped out of a ship, a naval ship. All the windings are removed and they're rewound. And a tender would have a rewind shop that could rewind motors up to 200 horsepower in size. And that's because of the marine environment, the saltwater environment is causing corrosion and things. If you don't do that, then by the 10th year, you're going to have motors out of commission that won't work. So you do it every 5 years based on at the end if you waited too long, that next 5 years you'd have motors burning up. I had a condensate motor, and this thing has 10 gauge wire on its stator. So if you think about the size of 10 gauge wire, what you'd normally use going to your stove or your hot water heater or your dryer. It quit running one day. Okay, so we took it apart. It had a hole going through those windings the size of a $50. We never smelled it. It didn't open a breaker. There was no overcurrent. We didn't see any fireballs going. And the space is manned 24/7. So those things can happen.
How big of a motor was it?
It was 10 horsepower. Yeah.
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 Wow.
So here's my stator, and what I have is each one of these guys has a winding going around it. So this would be an A, a B, a C, an A, a B, a C, an A, a B, a C going around there. And I'm chasing that magnetic field as it goes around with the rotor is chasing that magnetic field as each of these guys are changing from A to B to C. Now, a magnetic field is something that has a pattern associated with it, right? And that pattern might not be good. So we'll put in inner field windings that shape the size of the magnetic field. So on a bigger motor, you'd throw in another set of windings so that this magnetic field wouldn't interfere with the other one. And So now we're wound up. We've got some cord wrapping it so that it stays in place. We've got to wind the stator with copper wires that are not insulated. And then we go and dip and bake it in a lacquer solution for insulation. And we do that after the fact.
So they do that after every winding, or after every set of windings, or they do it after
No.
somebody does?
You do all the windings, dip and bake it in one case, and the baking is being done at about 500 degrees.
The coppers don't, when they wind, I mean,
Yeah.
they have a tendency of touching, but how do you keep them separated?
Yeah. The issue is, why do you care?
Okay.
Because if I have, so here I got a wire right here, and I got a phase going down it, right? And then I got a wire right next to it with A going down it, and I got a wire right next to it with A going down, and a wire going next to it with A going down. It doesn't matter that they're touching, they all have A going down it. What it matters is that they're not touching the housing, they're not touching the rotor. That would matter. Okay. But touching each other wouldn't be an issue because they all have phase A going that way.
Right.
Yeah, so there's not much. The difference. So so here I've got a pole. So that's a metal thing, and I'm going to wrap winding. I'm going to wrap wire around it like that, and I got 10,000 turns, and I have A going in this way, and it doesn't matter because A is going through the whole winding as it comes out. It's not gonna. Does the electric field? Oh, never mind.
Yes, never mind, it's better, yes.
Yeah. So the lacquer is not to keep them from touching each other on a pole,
People touching
but
the
to
other
teach,
surfaces.
teaching the other surfaces, right? Here are this is my rotor. So my rotor is going to have pieces of metal going through it. I'm going to have windings around it as well, but I'm not going to have any electricity going to my rotor. The fields induced are going to be induced in the rotor by the rotating magnetic field going around the stator. Now, if I have a synchronous motor, I am going to have windings going to the synchronous motor. I'm going to make a north-south magnet in my synchronous motor that's going to follow the other guy. But in a squirrel cage motor, I'm not going to do that. So here I've got steel laminations going through there, and that's what my conducting bars are, and they're gonna be where currents are going to flow to allow magnetic fields to form. The magnetic fields interacting with each other is what make the motor go round. This is a centrifugal switch. As I go faster, I at low RPM I'm not touching. At high RPM I am touching. Well, we don't really care about that. Now, how am I going to hook these guys up? This is a single phase motor. Now, let's look at. I have this hunk of winding here that's going to make my magnetic field. What's the resistance of that copper? 1,000 feet of it?
All depends on the size.
Not very much, right? So let's say just 1 ohm, just for the heck of it, right? Yeah, just for the heck of it. 1 ohm. Is V still equal to IR?
Yes.
So if I have 120 volts and I've got current and I got 1 ohm, then my current's going to be 120 amps. How many amps do you think a 14 gauge wire is rated for?
Like 15 amps.
15?
Something less than 120? Right. So what happens is that when you start the motor, it's going to want some starting winding so that it has some extra resistance. Now, once the motor starts rotating, then what's happening is that the magnetic fields are forming there and might change in voltage between my input voltage. The motor is acting as a generator. It's generating a back EMF. Now that instead of having 120 volts that you had difference when you turned it on, you may only have a 2 or 3 volt difference because the back EMF of the motor might be 115 volts, and now you have 120 in, 115 being generated by the motor. There's only a 5 volt difference. Now you're going to not draw as much current. Okay. Now, when we threw the variable speed controllers on the motors in the other room, that helps that situation out. There's no excess starting current when you're using a variable speed controller. It just comes up to speed, goes down to speed as the variable speed controller is doing it. But here I have different ways to hook up a single phase motor. Now this is a 3-phase motor, and if you look at the first piece of paper that we have in front of you that I passed out, and I'll see if I can find mine. And you've done this already in the shop, you just hadn't thought about it all that much. Open. All right, so these are, you have T1, T2, T3, T4, T5, T6. Let me do a copy and paste of this in the other guy. Okay, and you can visualize those things coming out of your motor in the other room. And we told you that you were at low voltage, and you had to use the low voltage settings, right? So what you did is you connected T6 and T4 and T5 together. So you had 3 wires to go in one spot. And then you hooked up T1 and T7 to L1. And then you hooked up T8 and T3 to L3. And then you hooked up T9 and T3 to L3. So what you end up doing in a low power configuration, low voltage configuration, which is anything less than 480 volts is low voltage, is you end up having your coils in parallel. So that'd be phase A, T1, and you have coils in parallel, phase B, T2. Your coils would be in parallel, phase C, T3. So that's what you've done. You've gone and hooked those guys together and hooked them up that way. Now if I go and do it again, and this time I want to hook it up for high voltage. What I end up doing, and of course I can't do this in the shop because I don't have any high voltage, but if I hook up T1, T4 to T7, T9 to T6, T8 to T5, and then I run T1 over to L1, T2 over to L2, T3 going to L3. So if this is 480 volts, because it's high voltage now, how many volts do I have across one of those coils? 1, 2, 3, 4, right? 120. So I got 120 volts going across one of those coils. If I was back in this configuration where I'm in parallel and I'm at 240 volts and I have 240 volts going like that, how many volts do I have across one of those coils? 120 volts. So in both the low voltage and the high voltage configuration, I end up, the coil that the motor has the same voltage across it. Okay, I manufactured it in such a way so I could go either way on it. All right, now we ask ourselves, what would happen if we had a delta wound motor? So now a delta wound motor would look like that. Don't be looking for it. And I'd hook up T1 phase A, T2 phase B, T3 phase C. Is this wound for high power or low power? High voltage, low voltage. High voltage. Okay, and then I go and I do the same thing, and if I wanted to wind it for low voltage, I'd put my windings in parallel. Now, why would I care that I was Y or delta connected?
Because you got one phase that's going to be basically a grounding phase, and you got two other phases that are your 480. You can get 480 from phase to phase, but you take the phase to ground, you basically get like 0 volts.
Yeah. If I go and took my delta guy and I had 480 across those two windings, I'd have 240 across each winding, right? But we just showed that we would only have we only had 120 across our windings when we were Y connected, right? So delta connected, I have more voltage across each of the windings. That may or may not be good. On a submarine, all our motors are delta connected, and there are no grounds in the AC system. And in theory, you could grab an AC wire, bare wire, and you can't get grounded. You can't get shocked because there's no path to ground. In practice, there is a path to ground. It's a capacitive path caused by the wires being close to each other in our wire runs, and you would in fact die if you did something like that. But it makes it safer, even though it may not be. But the delta wound motor is more efficient than the Y wound motor. So if I have a 50 horsepower circulation fan for my air conditioning system, I would like it to run delta because that's more efficient. But I don't want it to start as a delta motor because that would be too much voltage and too much current being drawn. So what I end up doing on motors that are greater than 5 horsepower is I end up having a control system that starts the motor off as a Y wound motor, and then when it gets to speed, shifts it to a delta wound motor. So I look at these things here, and I have okay, T1, T2, T3, T4. So I'm going to break these windings there. So T1, T4, T5, T6, T7, T8, T9. And so now I can run it through a bunch of contactors and start it as a Y connected motor, and when it gets close to that speed, have it 2 seconds later or whatever, I can shift it to a delta wound motor and run it that way, just to be more efficient. Okay, so there's my delta wound motor, and again I can be in parallel. I can be at high. This would be a high voltage configuration. That's the high voltage configuration for my Y. Okay, I've got some mounting bolts, some louvers, some hole for my shaft, some bearings. This is a speed thing. Normally, when I'm running, I'm running between a no load speed and a full load speed. So I'm drawing some torque, and I'm slowing down as I'm getting to full load. When I get to an overload situation, my torque goes down and I start stopping, and I stall out. So I've got some rated torque the motor can go to. If I go above that rated torque, I start slowing down. So I can bind up that motor and stop it. That's not good for the motor. Okay, so but I'm running from a small. I'm not running from 1,200 RPM to 0. I'm running from 1,200 RPM to 1,150 RPM for full and no load on that motor. And then if I overload the motor, then I'd be bad. Okay, now we have 3 phases to worry about. I guess we don't. This is a single phase motor, and I've got a starting winding thrown in, and to keep the currents down. And then when I get fast enough, a centrifugal switch happens so that I turn off the starting winding. And there's a difference in phase between the starting winding and the running winding. And that difference in phase is what's going to keep me from going over currents and burning the thing up. In general, in a normal manufacturing center, you're not going to have a single phase AC motor. That isn't going to work. You're going to have 3-phase motors everywhere in the plant. But your swimming pool might have one of these. So you could have a half horsepower motor on your swimming pool. That's what it's doing. We can also throw in a capacitor. So this is a capacitive start guy. It's got a starting winding and a capacitor that has to charge, and there's going to be a change between the starting current and the running current. Those capacitors are bigger than my fist in general, a little bit longer. They sit on top of the motor. Last a long time, but they may have to be replaced. So that would be something that you could do.
Units, outside compressors have them.
Yeah, exactly. Here I have 2 capacitance. So I'm a capacitor start, capacitor run, capacitive starting, but I also can switch over and there will be a capacitor in the run cycle too. I have a shaded pole motor. So I have a pole. This is causing north and south, and it's changing back and forth. And I've got one that I throw an extra winding around there, so I'm shading the magnetic field to change the shape of the magnetic field for the motor. So I got a main pole, and then I have one that's shaded. I'm going to throw a winding around it to have it be a little bit different. Clearly, in the manufacturing process, I don't want to do that, but when I get bigger motors, I don't have a choice. So now we're seeing that field movement between the shaded and unshaded poles. So my shaded poles are doing that, my unshaded poles are doing this, but when we put them together, now I have a magnetic field that goes directly across with a nice equal flux. Okay, well here's my phase A, B, and C. In the 3-phase wiring lab that's in L144, we brought in phase A, B, and C from the fuse panel. In the wiring lab you guys use in 133, I plug it into the wall. So the 3 phases are being just plugged into regular AC outlets on the wall. When I went to find where my A, B, and C was, how did I know? I hooked up an oscilloscope and I looked at it. And the 2 that were 120 out of phase, they're the right 2, and the next 2, if he's 180 out of phase with that one, 120 out of phase with him, then that would be the C guy. If he's the same, he's wrong. If he's the A guy, he's wrong because he'd only be 120 out. So I'd go and that's what I did. It was trial and error, and that's why they're plugged in where they're plugged in. Want to hose somebody over someday? Plug them into a different plug. Okay, so here we are. We're bringing in a Y connection and delta connection. As you recall, or you didn't recall, depending on whether you recall or not, we did in circuit analysis some Y to delta conversions. They were a pain in the rear end. There were 12 different numbers that had to be put in, but you can do that. You can, given a Y circuit, calculate what the delta currents are going to be. That's not something we're going to do in this class, but it can be done. This is speed torque for a normal three-phase motor application. So with all three phases going, you have a nice curve, fully loaded. If you go in and drop one of the phases, then you're a single-phase motor. You look just like the single-phase guy. If you had two of the phases, then something like that would happen, which is kind of weird. But with all three phases going, then you have a nice, smooth speed line, and there's no stalling going on. This is how I'm going to move clockwise or counterclockwise. So I'm wired T1, T2, T3. I'm going to go clockwise. If I'm wired T2, T1, T3, then I'm going to go counterclockwise. So my motor doesn't care which way it's rotating. It'll depend on how you wire it. The water would care. The beer would care. The malt would care. Whatever it is. The paint would care if the pump went the wrong way, right?
Yeah.
So don't be rotating your motors the wrong way. So this is a percent full load torque and the current that I'm drawing. So I'm drawing 100 amps. I'm probably opening a breaker someplace. Full load was down there someplace. So at full load, I'm only drawing 5 amps, but I could go and have considerably more being drawn until I break my motor. Okay, here's a motor that's looks like it's AC start, looks like Y start and delta the other way. No. Yeah, I'm not sure what that is, so we'll just skip it. This is what my pole's going to look like. Okay, this is metal with wire wrapped around it. Now I have those same poles sitting there on something that's going to rotate around. So I'm going to rotate wires around inside there. DC exciter circuit. In a synchronous motor, I'm going to use DC to make a magnetic field on the rotor, and then that magnetic, the motor will follow the magnetic field of the three-phase around, and it gets power by the number of degrees it's away from that magnetic field. So if it's following it exactly, then you have no torque. If you have a couple degrees difference, then you're getting more and more torque, 15 degrees difference. If you slip a pole, then you try to get too much torque out of it, you just wrecked it. So you don't want it to slip poles. That would not be good. So here we are hooked up, three-phase, hooked up to something. Synchronous motor stuff. Rotating field, exciting in a synchronous motor. Okay, so same type of thing. Delta connected voltages, high voltage on top, low voltage on the bottom. The motor's going to have associated with it a wiring chart. So you're not memorizing this. It's not going to change. You could memorize this. But the day you take your memorization and hook it up to the motor is the day you did it wrong. Make sure you look at the chart on the motor as you're wiring it. Here's a Y connected guy. We're doing the same thing. High voltage and low voltage. I already did that. three-phase motor controller stuff. And delta connections, Y connections. You're going to have, on your motor nameplate data, you're going to have things that will tell you stuff. How many amps can it take? How big is it? And I can buy a motor any size I want. They're all sitting on a shelf someplace. Johnson Supply has motors up the yin yang always. And, so now we're gonna go and make the motor roll. So we have some controller turning on the AC motor, some operator turning it on. Now what we're doing is we're going to go and use a variable voltage to drive the motor. So we're going to send in digital signals pretending to make a AC signal from some device, whatever it is. So that's similar to our voltage, our variable frequency guy. We're simulating AC signals by putting ones and zeros on the wire, is what we're doing. So now I'm going, and this is a pattern, and I have I'm on a little bit, so I get a little bit. I'm on a little bit more, I get a little bit more. I'm on a whole lot. Now I got higher voltage. So I'm doing a pulse modulation, a pulse width modulation of the signal to simulate a AC signal. That's what I'm going to do. And now I can change the speed because I can change the speed of my pulse modulation. That's exactly what your variable speed controller is doing. If you would take the variable, and we'll do that sometime, take the variable speed controller and hook it up to our oscilloscopes, you'll see zippo, zappo, nothing. Our oscilloscopes in the lab are too slow. But I have two oscilloscopes that are 100 megahertz oscilloscopes. You can, and they're storage scopes. You can store this pattern, and you can actually see it. But the 20 megahertz scopes, which are normal for our lab, that I have a lot of, it's just going to have that be an AC signal is what you're going to see. You're not going to be able to see the other part of the signal. So now I'm changing my frequency, and I'm doing a frequency control of the motor. Oh, look at that. It's a PowerFlex 40. I've seen that before. I don't know where. This guy's obviously on some network port. Oh, we're done. All right, so now we got to go back to the handout that I passed out. So we already did page 1, and now we have to look at page 2. So, how do I get the electricity into the plant? I've got thousands of volts coming into the plant. I'm only using 480 going into the motors. I got to do something about it. So I've got transformers. So on the top part I have transformers, and on the bottom part I have things that are hooked up to the transformers. Okay. So now it's a matter of being able to do that, and whether or not I can find this printout. How do you spell industrial electronics? With one I or two? Oh, very good. I know, it makes it look like I've been doing this forever, right? Yeah, I probably have.
So each transformer, you basically supply an A, a B, and then you go from B to C.
All right, so what I have here is I have an A, B, and a C wire coming in at 10,000 volts. And it says complete the transformer wiring according to a delta transformer bank. Okay, so I'm doing a delta. Okay, so that means I have to go from A to the transformer. I have to go B. I have to go B. I have to go C. I have to go C. I have to go back to A. So that would be a delta winding of the primary side of the transformer. And now I want a delta winding of the secondary side of the transformer. Will be connected to a distribution system to form a delta primary. Okay. Indicate how the secondary transformer lines will be connected to the distribution system that will provide three-phase high voltage, low voltage signals. Okay, so we've come in delta. Now we're going to leave delta. Okay, so how are we going to do that? Well, we'll hook those two guys together, bring them to A. Those two guys together, bring them to B. Those two guys together, bring them to B. Those two guys together, bring them to C. These two guys together, bring them to C. Those two guys together, bring them back into A. Okay, so now we have a delta winding of the transformer, both on the primary and the secondary side. All right, now we want to, as much as possible, notice that I haven't hooked up anything to a ground yet. I don't intend to hook up anything to a ground either. All right, so this guy's a three-phase motor. I'm going to hook him up phase A, phase B, phase C. This guy is a two-phase motor. I'm going to hook him up phase A, phase B. This guy is a single-phase motor. I'm going to hook him up phase C to ground. Over here I have lights going on. Those are probably lights. So I've got A, B, C, A, B, C, ground. So I would probably hook these guys up to whoever I want to. But I wouldn't go and go A, B, C, A, B, A, B, A, B. I wouldn't do that. And the reason is that I have to have the same currents flowing through all three phases. So I want my three phases to be loaded and balanced. If my three phases are not loaded, not loaded the same, not balanced the same, I'm drawing circulating currents from the power company, which is making the merry-go roundy, and they're charging me for it anyway. Okay? So, and I don't want that. All right. So that was a hookup delta on the transformer. All right, next guy. What happened to? Oh, there they are. I found it. Okay, now the instructions say complete the wiring diagram Y to Y. All right, Y to Y. Okay, I'm going to take a wire and hook him up there. I'm going to hook him up here. I'm going to hook him up there. And then I'm going to take another wire, A to A, B to B, C to C. Okay, so now I'm hooked up Y on the primary side. Can you see the Y? Why do I have to show you a Y? Did you see the delta in the first guy? Maybe, maybe not. Okay. So now I'm gonna hook up the other side, and I want to be in Y again. So I'm gonna hook up this guy to that guy to this guy. Oh, that's wrong.
Should it be one winding and another winding?
That's wrong. Let me think about this for a moment. Okay, I got it. Hook up those two to those two. To those two. I'm going to come A to A, B to B, C to C. Okay, so now I'm Y connected primary, I'm Y connected secondary, and now I can run my motors to phase A, phase B, phase C. I'll go A to B, C to ground, and I'll hook up control power. Or it might be the lighting panel, it's hard to say. Okay, so that's 10, 10-1, 10-2. 10-3 says I want delta on the primary, Y on the secondary, and 10-3 says I want Y on the primary and delta on the secondary. So we'd end up doing the same thing we just did, except differently. Okay? So if you can do 1 and 2, you can do 3 and 4.
Colorful.
All right, now, clearly we've had you wire things in the lab, right? Well, on a test, we're going to have to wire things on paper. So that's what the next project's all about, wiring something on paper. So we'll look at this guy first and do several of these. All right, so I want to complete the wiring diagram, start, stop, switch, blah, blah, blah. Okay, so I've got ladder logic down here, and it says I'm coming from L. You don't have this guy. I'm coming from L1. Coming from L1 to the stop. So L1 to stop. Well, I'll do that one too. I just didn't print out 3. Where was I? And then I'm going to go from start to stop. And then I'm going to go from start to the motor. Start to the motor. And then I'm going to go from the motor to the overloads back to L2. Motor to the overloads. We'll change colors. Back to L2. And then we have the main line guy sitting there, the holding contact, which is here, and he's going to go across the start guy. So we're going to go across the start guy. Okay, so I push the button. I have current going to the start winding. The start winding starts, it closes. With the start winding closed, I now have a path that keeps me running when I let go of the stop button. And then I push the stop button, boom, the motor turns off. Say again? Well, first of all, you're a 6'4", and I'm doing 6'3". So I am bad. Okay, I'll go bring up 6'4" and do exactly what you have. But clearly, you're gonna. I'm not going to give you 6'4" or 6'3". Yeah. I'm going to give you something more complicated to do. Oh, it's almost the same. The only difference is you have a running light. Yeah. So I'm gonna go to 6'4" now. You notice the side of the room that looks directly at the screen has no problem with it. Just the guys on the peripheral over there. Notice that? No, is that? No, they're hosed. Okay.
Yeah.
As long as they're hosed, that's all that matters.
How long is it going to take for this thing to go on the web so I can pause it and then do
Well, it all depends. If there's a lot of questions asked and I don't get done, then probably be Friday. But if I get done at 11:45, then I got 15 minutes to do it. Oh, you mean the video? The video won't be up until after the test. Now, why is it? What am I not doing? Okay, so this is a picture. Yeah. Come I can't do a grabber thingy. Worksheet. How come the 4-10-3 guy worked? Oh, the 4-3 guy I put there. That's it. All right. So I gotta figure out how to do this different. Okay. So there we go. Copy. It's a computer thing. I gotta figure out how the computer works. Paste. Keep resolution. Oh yes. All right. Well, that is definitely helpful.
Can you see it?
Definitely helpful. Now I should be able to get that guy to go smaller if I can grab him. Oh, there we go. I can get him. I got him. Okay, so there we go. This is 6'4". So I look at the ladder diagram and I see I want to go from L1 to stop. Okay, so I'm going to go from L1, and right there there's a screw I can hook my wire onto. What color am I? I want to be black. And I'm going to come over here to the stop guide. And then I want to go from the stop guide to the start guide. So I'm going to do that. Then I'm going to change colors, and I'm going to go from start to the main motor. Start. Main motor. Main motor to the overloads. The overloads, I'm going to come back to L2. Notice that I'm not using control power like I do in my lab. I'm using L1 and L2 for my control power. So my components had better be better than the ones I have in my lab. Because in the lab I'm only using 120 volts. I'm using 240 or 480 when I go from L1 to L2, depending on if I'm in low or high voltage configuration. Okay, now I've got to hook up the normally open contact between the start guy. Okay, so I'm going to take the normally open guy and hook him up between the start. And that would be your 2 and your 3 on your main motor starter that you're dealing with. And then I got to make the pilot light come on. Now it looks like the pilot light is normally on, and when the motor starts, the pilot light goes off. That looks like what's happening here. So what color can I use? I can use black. Okay, so I'm going to go from L1 to the normally open switch to the green light.
Isn't that normally closed?
Normally closed, yeah. and then I'm going to go from the green light over to L2. And now we've run the wires associated with the ladder logic that's sitting there.
Can you go back to with the light? Light to L2.
Okay. Now this is where having crayons would be good, because they're nice and thick and they're different colors and easy for the instructor to see with his trifocals. Yeah. Or colored pencils would be good. Or a quad color pen is always a useful thing.
Or highlighter.
You notice that I didn't use white, right? Because there's no common. When you have control power, there's a common. I'd use a white. So I didn't use any white wire, and I didn't use any green wire either, because I'm not going to ground anywhere. So I didn't use any green, and I didn't use any white. Now, if anybody wants to know how I could have used white if I wanted to, we'll discuss that during lunch if you'd like to buy lunch for me. If not, I guess we'll. Okay, so now we'll do one more, and then we'll work the problems in Chapter 10. And that one's not cool. We want something, a kick-ass type one. 16.1. That looks really good. 16.1? No. Oh, maybe. Complete the wiring diagram. I don't care if you don't have it. I don't see where that matters. It's not relevant. I'm trying to find the hard one that's going to be on the test. Let's see. Oh, there we go. That's a good one. Oh. Copy. So that was good. That was helpful. Oh, that looks good. So now we have a wiring diagram we're doing, but our push buttons are one place and our controller's in a cabinet. And there's wires that are 500 feet long connecting the two, and we have to be able to say what we're doing. Okay? All right, so first thing we're going to do is we're going to hook up T1 to T1 and T2 to T2 and T3 to T3. So we're gonna hook up those guys first. Now at least I have power. Right. Because see, my motor is not here either. My motor is someplace else. So this is wires coming in from the motor, T1, T2, T3. I'm hooking them up to the controller. All right, so I did that first. I'm going to, from L1, I'm going to go to stop. I'm going to go to stop. Here's my stop guy. Where's L1? Okay, so here's L1 right there. And I'm going to run that over here to 1. Okay. Notice the 1 sitting right there. Okay, I'm going to call this 1. I'm going to come out 4. Why am I coming out 4? Well, because it says I came out 4. Okay, so I'm going to come out 4. I have one of these is start and the other one is jog. So this is going to be the start guy. It doesn't really matter which is which, right? Start guy. And this is going to be the jog guy. Jog. Okay. And the start guy is going to be hooked up to 4 and 5. 4 and 5. And the jog guy is going to be hooked up to 4. And is that a 3? 4 and 3. Okay. Notice that there's 2 and 3 sitting right there. See, though, that's the 2 and 3 on your normal controller thing. Okay, I'm going to change colors on you. Okay, I'm going to hook up 2. Where's the control? There's the control relay. So I'm going to hook up 2 to the control relay, and the control relay back to 4. Control relay. Oh, I'm outside the cabinet. What a bummer. Back to 4. I'm going to run 3. 3 is going to go to the control relay. Okay, so 3 is going to go to a contact on the control relay, which is there. And then from the contact on the control relay, I'm going to go to 4. Oh, I'm hosed. Alright, moving back. Take this guy off. Okay. I'm back up here. The other side of the control relay goes to L2. So this guy's got to come around to L2, which is right there. Okay, I'm looking at 3. 3 is going to go to three. Okay, that's fine. 3 is going to go to the main motor. Main motor start. 3 is going back to 3. Going back to 3 over there. And the 3 over there is coming over here to the jog guy. Okay, so that looks good. Alright, now I'm coming off of the 2 here, and I'm not coming to there. The 2 there does not go to where I have him. How did I get hooked up there? That's 5. 5. Oh, no, that was right. How come you guys let me take away a wire that was right? All right. What is that? That's 3. This is 5. 5 goes the control relay. 5, not 2. Okay, so it's 5 that's going to the control relay, which goes to T2. Alright, now I'm on 2 of the M guy. So the 2 of the M guy goes to the 3. The 3 of the M guy goes to the control relay, normally open. The 2 of the control of the main guy goes to the other one. he goes back to 4. He goes back to 4. This guy should be hooked up to 3 and 5. So there's 3. There's 5. Okay, so the only thing I don't have hooked up is the overloads. So the overloads are supposed to come from there back to L. The overloads. The overloads are already hooked up there. Okay, already hooked up there. So the overloads are going to there. All right, all done.
Actually, I understood most of it.
All right. So that's what you're running wires one at a time from the ladder logic into the picture. If I'm clever enough to give you one that puts it inside a cabinet, then you have to be smart enough to hook it up to terminal blocks instead of running the wires directly someplace else. Okay, well that leaves plenty of room to take points off, right? Yeah, I think so. All right. So I have 1, 2, 3, 4 problems to work. Okay, so I'm looking at problem number 1. What is the rotational speed of a 6-pole 60 hertz input? All right, number 1. So I got 6 poles, and I have 60 hertz. Well, if I'm at 60 hertz, and this is 60 cycles per second, right? And I go times 60 seconds per minute, then my rotational speed would be 3,600 RPM, revolutions per minute. Okay, so if I have a single pole application, that's what I would doing. That's what I would be doing. Huh? Yeah. So now, what happens if I have more than one pole? So I have 3 poles, 1, 2, 3, and I'm A, B, C. Then how quickly am I going to rotate through those 3 poles? Okay, so this guy's going to be north, and then that guy's going to be north, and then this guy's going to be north, and then that guy's going to be north. I'm going to be 3,600 RPM. But now, if I go to 6 poles, and I've got an A, and I got a B, and I got a C, and I've got a A, and I got a B, and I got a C, then I'm going to make it ABC in one cycle, the other ABC in the other cycle. I'm going to be running half that speed, 3,600 RPM, divided by 2. So I'm going to be running at 1,800 RPM if I have 6 poles. Now, the coal power plant south of town here has 36 poles. 36 poles. So that means to generate 60 hertz power, if you have 36 poles in your generator, you're going to go 3,600 RPM divided by those 36 poles divided by 3. That's a 12. That 12 goes into there 300 times. So he only has to rotate 300 RPM in order to generate that electrical power. So he's not going very fast to generate that electrical power because he has many poles generating it. Yeah, the more poles you are, the slower you're going to be. You need to go. All right, so that was problem number 1. Problem number 2. Use the speed calculation in number 1 to calculate the slip of a motor running at 1,000 RPM at no load. Okay, so we were supposed to be at 1,600 RPM, right? 1,800 RPM, but we're really going 1,000 RPM. So we're going to slip 800 revolutions per minute. But this, I'm pretty sure the slip is in per second. So we'll have to go back and look at my slip. Most of you have slips, right? You're wearing them now? Yeah, I figured it. That's the way it always is. Where's my slip bar? Okay. Slip is the speed of the rotating field minus the speed of rotation of the motor, and it's in RPM. Okay, so that's our answer. On page 482, we find that the slip is in RPM, and therefore our slip is 800 RPM. So the purpose of the industrial electronics class is to have you practice addition, multiplication, and division, right? Subtraction. Yeah, that's the whole purpose. Just another reinforcement of your math. All right, so as long as you know that, everything will be fine. Problem number 6. Approximate the full load, no load, and starting currents for a 100 horsepower, 480 volt, 3-phase induction motor. 100 horsepower. And 480 3-phase. Well, I got 4-0 for rewriting the problem right. Now, what are we going to do about it? How many watts in a horsepower? 760, 766, 765, 776.
Just did it.
Huh? Yeah, you just did it in physics, probably. I think so too. 776 watts per horsepower. So I got 100 horsepower. So that means I have 77.6 kilowatts. .6 kilowatts. Okay. So is power IV? Is power current times voltage? And the answer is yes. So the current has to be the power divided by the voltage. 7.6 kilowatts divided by 480 volts. Calculator. 77.6 E3 divided by 480. 161 amps. True or false? False. It's 3 phases, right? So we got to divide by 3. So the running full load current. Take that number, divide it by 3. We'll call it 54 amps. Okay, well that was good. That got one of 3 things. That's the full load. Now we need the no load and the starting currents. Alright, so I'm sure that V is equal to IR for both of them, but I'm also sure that there's some formula for calculating it, so we'll have to find the right page again. There's the power factor page. No, we don't want power factor. Full load, we got full load, no load. Okay, so current no load on page 500. 10 horsepower, 3-phase motor. Okay, so current no load, 0.3 times the current full load. Alright, so our answer from up above times 0.3, 16.2 amps. And then the starting current is going to be 6 times the full load current. So current starting 6 times current full load, 6 times 54, yeah, 6 times 54, 324 amps. Now that's why you'd want to put a variable speed controller on this, so you don't do that, right? That means you have to have breakers that won't open at 100 amps, you know, so that would be that. All right, well that seems reasonable. That was 6. Moving on to 8. Number 8. Calculate the real power. Okay, so if I look at voltage, and I look at current, and voltage times current is going to be something. I'm looking for the real power. So let's say I look at this is power, and this is imaginary power. So real power is down there, and apparent power is there, and that's going to be imaginary power. Now, your plant is mostly inductive because it has mostly motors in it, and so you want to throw in a capacitive bank to get rid of the imaginary currents that are flowing, so you only get charged for real power. All right, back to what we're doing. Calculate the real power. So I got 240 volt amps. What's a volt amp? A watt. Why didn't they just say watt? Right? Volts times amps is watts. Why do they call it volt amp? Well, because until it's goes to a meter, it's not a watt yet. So that's the way we do it. Okay. 3 phases, induction motor with a 90% power factor. A 90% power factor.
That sounds cool.
So this is the volt amp measurement is the apparent measurement, and that's why we call it volt amps. If it was real, then we'd call it watts. 90% power factor. Okay, so what do I want to find? The real power?
Yes.
Okay, so power real. Gee, I only have two numbers. 90% of 240 is, so basically I could either divide it by 90% or multiply it by 90%. Those are the only two things I can do. I couldn't add or subtract, right? So if I thought the real power was bigger than the apparent power, I would divide to make it bigger, but I think it's less, therefore I'm going to multiply it. 0.9 times 240. So my real power is 216 watts, and I would leave that in watts. That's 8. Number 11. What is the service factor of a 55 horsepower motor that can actually provide 75% horsepower to the load? Well, it's all in English, right? Yeah, what more do we want? I mean, why would we want a problem that wasn't written in English for? Okay, so I got 55 horsepower is my motor, but it can go all the way up to 75 horsepower, and we want to know the service factor. Yeah, I guess we only have two numbers, so we could probably just goof it off. Right? Service factor. I see the power factor. It's gotta be someplace. Efficiency, duty cycle, service factor. Service factor on page 513. The service factor is a rating that specifies how much a motor can be overloaded. For example, if the service factor is 1.2, that indicates that it can be overloaded by 20%. In other words, a 55 horsepower motor can actually do 6. Okay.
25 times 100.
So 20, the over, divided by 55, 20 divided by 55 gives me 0.36. 0.36. So that implies a service factor of 1.36. Now, if that is true, then I ought to be able to multiply 1.36 times 55 and get 75, right? I can. 1.36 times 55, and I get 75, yes. Okay. So that's how I would do that problem. Okay, any questions?
So there's 1.36.
What?
What was that referring to, man?
No, that would be something that go on nameplate data. So I buy a 1 horsepower motor with a service factor of 1.5. That would mean that it could do 1.5 horsepower before it burns up. Okay, so it's sort of a guarantee thing. So when I build a plant, I always have a design margin. So the roof of this building is supposed to be able to hold up 10,000 pounds per square inch, okay, based on having a 150-foot snowstorm or something.
Mm-hmm.
Well, I want to design the building to be 150% better. I'd want a design margin thrown in, so that if the snowstorm happened while the electronics class was standing on top of the roof, it would still hold the weight, type thing. So in a nuclear power plant, it's typical to have design margins of 2. So the plant is going to 1,600 pounds per square inch. That's its normal operating pressures, but it's not going to break if you went twice as much. So it could go to 3,200 pounds per square inch and not break it. That's the design margin. So when I build my bomb shelter, right, I want to build it so that it'll survive a nuclear weapon blowing up a mile away. That'd be easy to do. If I wanted to survive a nuclear weapon blowing up within feet of my bomb shelter, then I'd have to do something different. Yeah, exactly. I want a different design margin.
I was gonna do